Okay, welcome back. So I left you with this question to work out how many times bigger a red giant star up here in the HR diagram is than a red dwarf star down here. So hopefully you recalled that the relationship that we need between luminosity, radius, and temperature of a star is this one. So that luminosity is the surface area, 4 pi r squared, times sigma 2 to the fourth, the part that comes from the energy output of a black body. So as I mentioned, then we don't need to worry about the absolute values here. We're just interested in scaling these two stars together. Okay, so that means we only really need to look at the proportionality. So that L is proportional to r squared 2 to the fourth. So then if we've got two stars, we can just divide this equation for each one, if you like. And this is quite a common trick that you can do throughout this module. Often we're just comparing one star to another star, and so you can just scale the two and all the constants drop out rather than having to worry about going and calculating the actual values and then comparing them. Okay, so we're comparing the red giant star on the top line here to the red dwarf on the bottom line. Now, I set the problem up telling you that basically we assume they're both the same temperature because we're looking at a vertical line in the HR diagram. So temperature is the same for both stars. So that term goes to unity. Okay, so simplifying down again. And we're interested in the ratio of the sizes, so the ratio of the radii of the two stars. So we can turn this equation around to look at the radius of the red giant compared to the red dwarf star. And you can see that it's just proportional to the square root of the ratio of their luminosities. And the ratio of their luminosities is 10 to the 2 over 10 to the minus 4, so that's 10 to the 6 is the ratio. So the square root of that is just 10 to the 3. Okay. So that's telling us that the radius of the red giant star is 1,000 times bigger than the radius of the red dwarf star. Okay, so if we go back here, so this star up here is 1,000 times bigger than this one down here. And the same would be true for any, sort of magnitude. So a star up here is actually 1,000 times bigger than the sun, okay, because it's still 1,000,000 times more luminous. So these supergiant stars are 1,000 times bigger than the sun. That would mean their radius is, out here past the orbit of the Earth, pretty much. Yeah, 710 to the 8 to 710 to the 11. Yeah, it's most of the way to Jupiter. Okay. So now you can see why these are called supergiant stars. They're absolutely enormous. Okay. And these are giant stars because anything above the main sequence will be bigger than the stars on the main sequence. And the contrary is also true. So over here, if you go like here, if we compare the star Vega to one of these white dwarfs down here, these white dwarfs would be 1,000 times smaller, okay, pretty much. Yeah, not quite, but nearly. So these are very, very small stars, much, much smaller than the main sequence stars. So that's manipulating that equation. So we can put that into action. You can see the proportionality here. L is proportional to r squared 2 to the fourth. Now, we've already said that the HR diagram is basically a plot of luminosity versus effective temperature. And it's a log plot. So it's a plot of log L versus log T. Okay. And so again, if you look at, if you take the logs of this kind of formula, then you would see that that would then be a straight line. You'd have L equals 4, log L equals 4 and log T. Okay. And because temperature is going in the reverse direction on the HR diagram, you'd have a slope of -4 in there if radius was constant. And we can see that on this next diagram. So this is just another version of the HR diagram, luminosity against temperature going backwards. But now we've got lines of constant radius on here. So it's really just applying that proportionality that I just talked about. So the slope of this line here is about -4. Okay, so you can see for for 1 order of magnitude in temperature, we're dropping 4 orders of magnitude in luminosity. Okay, so that's what's going on there. So you've got these straight lines in the HR diagram of constant radius. So obviously the sun here is at 1 solar radius, and you can see that most of the main sequence stars are fairly similar size to the sun. So as you go up in temperature, then they get a bit bigger. And as you go down in temperature, they get a bit smaller, quite a bit smaller eventually, more than 10 times smaller. But you know, a lot of the common stars around here are very similar size to the sun. So you can see already here that if we go to the giants, the red giants, then they're 10 to 100 times bigger than the sun. If we go to the supergiants, they're 100 to 1,000 times bigger than the sun. Okay. And if we go to the white dwarfs, you can see they're all actually about 100th the size of the sun. And we'll come back to that in one of the problems later. Okay, so these are, you can see why these are dwarfs, these are giants, and these are supergiants, because they're all going this way in the diagram, getting bigger and bigger with size. Okay. So that, I just want to now finish off a little bit of notation, because we weren't quite finished with sort of stellar classification. So earlier we talked about the spectral type in terms of the temperature classification with the O, B, A type classes. But normally you will also see some more notation associated with spectral type, which is actually to do with this luminosity classification. So it's to do with basically the size of the star. So a different bit of physics comes in here. And we're going to, again, use some information that comes from the spectrum. But this is to do with the actual sort of width of the spectral lines, not their depth, but the width. Okay. So don't get too worried about the details here, because we're not really going to worry about the physics behind it, but I just want to outline it a little bit. So in a literally a hand wavy sort of way, then if you take a star like the sun and turn it into a red giant, it'll become much bigger, but it'll basically have the same mass. You've just taken the same mass and distributed it over a larger volume. So that would mean that the average density of the star goes down, including the density of gas in the atmosphere of the star, the photosphere, where the spectral lines are being formed. Okay. Now, if you go down to the sort of atomic level and think about, well, let's just think about atoms for a moment, atoms of hydrogen in the atmosphere of the sun, for instance. So we've got atoms moving around. Every now and again, they will come close to each other and collide. Okay. Now, if the density of gas is very high, then that collision is going to take place more often. Okay. As you spread the gas out at lower density, then you're going to get less collisions, because they're not, the atoms aren't going to encounter each other so often. Okay, so that means that you've got less collisions. Now, what happens, coming back to the quantum structure idea here, thinking about the energy level diagram for hydrogen, what happens when you bring 2 hydrogen atoms close together? Okay. Well, they've got charges and everything, and so the influence of one atom is going to influence the electron orbiting the other atom. And so when you bring 2 atoms close together, they interfere with the sort of orbital structure of the electrons, which changes the energy levels a little bit in each atom. So if you change the energy levels, okay, if you change the distance between the energy levels, then you're going to change the wavelength of the spectral line that is emitted from between those 2 levels. Okay. So, just to recap, if we increase the density, we've got more collisions, we've got more disturbance of the energy levels, and therefore you're going to get slightly different wavelengths for your spectral line compared to if you've got a lower density situation. So when you average that over a big population of atoms, it basically means that you change the width of the spectral line, because there's a whole different range of wavelengths contributing to the spectral line rather than just a narrow range of wavelengths. So that just changes the width of the line. So basically, the denser the gas, the broader the line. Also, the denser the gas, the smaller the star, effectively. So that leads to a way of, again, using different information here from the spectrum. So just using the width of the spectral line rather than its depth for a luminosity class. Okay. We can see that in the example here. So here are two spectra from two stars that have got the same temperature. Okay, they're both a B8 spectral classification. So the B8 is telling us what the temperature of the star is. Okay, so that would be a fairly hot star, 20,000 Kelvin, something like that. But if you look at the spectrum here, you can see that again, you've got examples of two of the Balmer lines here. But the Balmer line in this star, the top one, is much, much narrower than the Balmer line in this one, which is much broader. And that's because this one is a main sequence star, and this is one of these supergiant stars, much, much bigger. Okay. So you can see that the same pattern of lines is present, which means it's the same temperature. Okay. So you can see other lines here, they're all present. Okay. So the temperature is the same. So the only thing that's different is the atmosphere is more rarefied in this top spectrum, and that you get less of this bouncing together of the atoms, disturbing the energy levels. So the wavelength of the Balmer lines here is much more well defined than it is here. Okay, so this line width was used again quite early on to classify, again pretty much originally without really knowing much about what was going on, but classifying the luminosity of the star. So that leads to a little bit more terminology. You could already see it in action there. So as well as the spectral type for temperature, which was the letter followed by a number, like B8 in that previous example, you will usually see a Roman numeral attached on the end of that designation. Okay. And that Roman numeral could be anything from 1, 2, 3, 4, 5, or even 6. This is pretty rare. But for this module, then common ones that we will see are the Roman numeral class 5. Basically, that corresponds to the main sequence. Okay, so again, here's a jar diagram with where you find these luminosity classifications on it. Okay, so here's anything on the main sequence would be luminosity class 5. So they would have those sort of broad lines like I just showed you on the bottom spectrum. Anything above that is going to be more luminous. And so you've got various types of giants. Again, don't get hung up on all the different, in fact, you don't really need to get hung up on much of this, really. So you've got giants here, so they're like Roman numeral class 3, and you've got the supergiants, Roman numeral class 1. So if you go back to that previous example, then this is a supergiant because it's got the narrowest lines, and this is and that's given the Roman numeral 1. And here we've got sort of dwarf idea or main sequence idea. So again, a bit of confusing terminology. So this class 5, often referred to as dwarfs, but it means main sequence. White dwarfs are not in this classification scheme. Well, if they are, they'll be over here in class 6, which would be down here somewhere. Okay, so that completes the sort of spectral classification thing. So we'll come across this notation a few times, but I'm not really going to be testing you on it. We'll come across it in the workshops more than anything. Okay, so next I want to bring in a parameter we haven't talked too much about yet, which is the mass of the stars. Okay. And again, it's a little bit chicken and egg in the module here. So we're going to find out a way of determining mass when we finally come on to binary stars in a few lectures' time, because that's how you actually determine the mass of a star. But for now, I'm just going to quote a result at you and then show you later, in a sense, the method that is used for determining the masses. So for now, let's just take this as red. Okay. So when you determine the masses of stars, again, of course, a good thing to do, like any scientist, is plot one parameter against another one. So if you plot the luminosity of a star against its mass, you find that there's a reasonable sort of power law relationship between them. Okay, so it's approximately that the luminosity goes as mass to the power 3.3. Okay. This is an average. It does wobble around a little bit, but for the purposes of this module, then this is what you need to use. Okay. So the luminosity of a star is proportional to mass to the 3.3, but a very big but. This only applies to main sequence stars. Never apply this relationship to any old star if you don't know what it is. Okay, I mean, if it's a giant or a white dwarf, then this relationship does not work at all. Okay, so you can only apply it to main sequence stars. So this relationship is only true for main sequence stars. So you've got this proportionality here. Okay. Again, we can bring in this idea of just scaling everything to the sun to turn it into an equation rather than a proportionality. So you can turn it into an equation. Again, I've used a twiddles rather than equals here because it is a fairly approximate power law, but it's good enough for us. Okay, so that the luminosity in solar units is equal to the mass in solar units to the power 3.3. That's the way to use that. Okay. So let's have a look at where that sort of relationship comes from. So here's an example of the data, again, from a diagram from the universe textbook. So again, each point here represents a different star that has had its mass accurately measured and plotted against its luminosity, again, on a log-log scale. Okay, so a straight line through here would indicate a power law relationship. And you can see that certainly up through this part here, there's a pretty good power law relationship. Well, all the way through, it's a fairly good one. Okay. And if you see like 1 order of magnitude in mass here, corresponds to 3 orders of magnitude or more in luminosity. So if you go up 1 order of magnitude in mass, you're going up over 3 orders of magnitude in luminosity. So that's where the power law 3.3 comes in. So you can think of 3.3 as the average slope of this line across all stars. That's another way of thinking about it. Okay. So you can start to see on here, but again, just for main sequence stars, no other stars. Other stars would not fall on this relation. So you can start to see the range of masses of stars here. So here's the sun, obviously, at 1 solar mass, but there are stars, way over 10 times more massive, and there are stars down here that are 10 times less massive. So let's have a little think about that for a moment. Okay, well, let's do this first. So let's put those stellar masses now and put them back on a HR diagram to illustrate something here. So each point now is labeled with its mass. So you can see that this main sequence here, so again, it's a HR diagram, temperature this way, luminosity this way. The main sequence is also a sequence in mass. You've got low mass stars down here at the low luminosity cool end, and you've got high mass stars at the high luminosity hot end. Okay? So this is now starting to tell us something about the origin behind the main sequence, really. So stars of different masses find themselves at different points on the main sequence. Okay. Now, probably a good time now to try and dispel a common misconception, is that the main sequence is somehow a time sequence. It's nothing to do with time. Okay, the sun, which is sitting here at this location, 6,000 Kelvin and 1 solar luminosity, is not going to change over its main sequence lifetime, the time it spends on at this main sequence location. It's just going to sit there. It's not going to move up or down this sequence. It's just going to stay there. So once a star is born with a particular mass, that determines where on this main sequence the star sits and stays. Okay. Okay, so let's now just have a quick think about the range of these main sequence masses. Why do we get stars within this sort of range of masses? Okay. So let's start at the lower end. Okay, so the lowest mass star that we ever find in this sort of main sequence location is just below a tenth of a solar mass, about 0.08 solar masses. Okay. So why do we not get stars of any lower mass? Well, it comes to the sort of very definition of what a star is. A star needs to be powered by nuclear fusion. Okay. And nuclear fusion requires extreme temperature and density. Okay. So, we talked about our sun. It's got a pressure of 1 billion atmospheres in the center of the core, and it's got a temperature of 10 million Kelvin. What happens as you go to lower and lower mass stars? Well, as you go to lower and lower mass stars, obviously the sort of gravitational pull of the star inwards, keeping everything together, is getting less because you've got less mass. If you've got less mass to kind of keep up and keep stable against gravity, you don't need such extreme temperatures in the core of the star to keep the star balanced. Remember, we talked about the idea that stars like the sun, all stars on the main sequence, are held up just by the thermal pressure of the gas. So if you've got less mass, you've got less gravity, therefore you need less temperature in the core in order to keep the star up. At some point, as you go down to lower and lower masses, the star will get so low in mass that its core temperature will be so low that fusion can simply not take place. Basically, when the core temperature drops below less than a sort of million Kelvin, something like that, hydrogen fusion will just not take place. You can't get the protons to fuse together. It's just the gas is too cool. So that explains why there is a lower limit to the masses of stars. Okay. So below that, stars are never hot enough to burn hydrogen, to fuse hydrogen. Now, it doesn't mean that objects with lower masses than that don't exist. It's just that they're not really stars, okay, because they're not fusing hydrogen. And in fact, again, in the last sort of 20, 30 years, we now know that there are many, many objects out there in our galaxy and everywhere that do exist with masses below 0.08 solar masses. And they're referred to as brown dwarf. Okay, sometimes they're even called brown dwarf stars, which is a bit of a misnomer. They're basically brown dwarfs. Okay, so these are kind of failed stars. Okay, so they can have masses between, all the way down to like 1,000th of the mass of the sun and up to this limit of 0.08. Okay, so they would be referred to as brown dwarfs. So they exist, you can see them. Certainly when they're young, they're actually shining away due to gravitational potential energy. They're just slowly shrinking, keeps the gas hot, they shine, they cool down, fade over time. But when they're young and still relatively hot, you can see them, temperatures of a couple of thousand Kelvin, that kind of thing. So they exist, but they're not stars. Okay, what about the top end? So the top end, a bit less well-defined, but around about 100 solar masses. Okay. So what's happening there? Why do we not get stars more massive than 100 solar masses? Okay. Well, the clue is in that mass-luminosity relation that we just saw. So you can see that the luminosity is going up with m to the 3.3, and that we were already, at the top end of the HR diagram, we're already up at 1 million times more luminous than the sun. So by the time you get to this very massive, very luminous type of star, you've got a huge amount of radiation flowing out through the atmosphere of the star. Now, a feature of radiation is that it can exert a pressure on gas, okay? Because photons, they may be zero rest mass, but they aren't, doesn't mean they don't have momentum, okay? So a photon has energy, so therefore energy and mass are equivalent, according to Einstein. So if you've got some energy, you've got some mass, and you're moving at the speed of light, you've got some momentum. Okay, so photons have momentum, and when a photon hits and gets absorbed by an atom, it will push that atom a little bit, giving the atom some momentum. So that is radiation pressure. Right? Okay, rate of change of momentum is a force. Okay, so radiation can exert a pressure. So, as I think I mentioned a while back, then radiation pressure in the centers of normal stars is not a problem, but in the atmospheres of these very luminous stars, very massive stars, it is a problem. So if you try and make a star more massive than 100 solar masses, you can't do it. It'll just blow the atmosphere clean off. So you just literally can't pile any more mass onto it. So the limit at the top end is set by radiation pressure, and any stars more massive than that would basically blow themselves apart. Not explosively, but generally. So that explains this range of 3 orders of magnitude in masses. I've just added another little point on here. You might have noticed it on a previous plot, I'll go back to it in a moment, that there are basically many more low mass stars than there are high mass stars in terms of on the main sequence. Okay. So stars lower mass than the sun are extremely common. There are lots and lots of them. As you go to higher and higher masses, they're quite rare. Okay. So you might want to make the analogy with like sort of sand on a beach. Lots and lots of tiny grains of sand, quite a few sort of pebbles, but not very many boulders. That kind of distribution of mass and size. It also applies to stars. Okay. So let me just quickly zip back to that relevant plot, which was this one. So this was a plot of all the stars in a volume of space in the solar neighborhood. And you can see it here, lots and lots of points down here at the bottom end of the main sequence, so the low mass end, as we now know. At the high mass end, as you get higher and higher up here, they get very rare, quite difficult to find them. Okay. And so that's true all the way through here. Okay. Go back to where we were. Okay, so last point before the next break. Let's have a look at another key idea here now, a lot of key ideas in this lecture, is this idea of main sequence lifetime. So how long would a star spend on the main sequence? So actually something I haven't said yet really is that we understand this main sequence as when a star is first formed out of basically a big ball of hydrogen, it will, it starts its life on the main sequence. Okay. So when a star is born, we'll come back to that later in the module, then it will start to burn its hydrogen fuel, but basically determined by its mass is where it will sit on the main sequence in the HR diagram. So the mass will determine its luminosity. Okay, so we've already seen a little bit of this before when we talked about the sun initially. So the idea about how long is it going to spend burning hydrogen, which is what we really mean by main sequence lifetime. Okay, so we saw that the main sequence lifetime, I'm giving it the symbol tau here, ms, is equal to the total amount of energy available from fusing hydrogen into helium, determined by the rate at which energy is lost, which is the luminosity. Okay. So we've already seen that energy comes from E equals mc squared, or the delta M. Okay. And we saw in the sun that there's 10% of the mass is in the core of the star available to burn. And if we make the assumption, and it turns out to be a good one, that 10% fraction is the same for all masses of stars, that 10% is the core mass where fusion can take place, then it basically means that the amount of energy available is proportional to the total mass of the star. So E up here will be proportional to M. Now we've also just seen that the luminosity on the bottom here is proportional to M to the 3.3. This is your mass luminosity relation for main sequence stars. Okay. So we can take this equation and turn it into a proportionality on mass. Okay, so main sequence lifetime is going to be proportional to M over L. but L is proportional to m to the 3.3. So you've got m over m to the 3.3, which means the main sequence lifetime is proportional to m to the minus 2.3. Okay. So what is this telling us? Well, this is saying that the more massive your star is, the shorter its main sequence lifetime. Or the more massive a star is, the faster it's going to burn through its hydrogen. So again, you can probably understand that, as we just talked about. The more massive a star is, the hotter its core temperature is to resist the increased gravity. The hotter the core temperature, the faster and better those fusion reactions go. And so that's going to generate more energy per unit time, which gets radiated away. Okay. So massive stars spend much less time on the main sequence than low mass stars. It's the key point for this part of the lecture. And as always, you can now go and prove this to yourself. So we've seen the range of masses, 0.08 solar masses at the bottom end, 100 solar masses at the top end, minimum and maximum mass of the stars. So just use that scaling we've just introduced. Again, you don't need to go through all the rigmarole we did for the sun. You just need to take that proportionality. Tau main sequence is proportional to the mass to the minus 2.3. Main sequence lifetime for the sun in years was 10 to the 10. Okay. So just calculate the main sequence lifetime for the 0.08 solar mass star and the 100 solar mass star in years, just by scaling using their masses according to that equation. Okay, and have a go at that, and we'll see you after a bit.